Welcome to The Explainer. We're all about breaking down big, complex topics into explainers that are clear and hopefully pretty engaging.
So, what really pulls the strings when it comes to our climate? The answer is this huge, intricate puzzle, way more complex than you might think. Today, we're going to piece together the real science of climatology. We're moving beyond the headlines to get a handle on the massive forces at play, the ones that have shaped our world for ages and are still shaping it right now. Okay, so first things first, before we can even start putting the puzzle together, we've got to understand what climatology is. What makes it such a unique and, honestly, a really challenging field of science? So, climatology, it's all about the long game. Think of it as studying the personality of a place over decades or even centuries. It's not about whether you'll need an umbrella tomorrow. That's weather. This is about the deep, underlying patterns that define a region. And this difference is so important. You've got climatology on one side. That's geography. It's looking at those long, slow patterns in a specific area. Then you have meteorology on the other side. That's pure physics, you know? It's all about the atmosphere's immediate, fast-moving behavior. And this quote from climatologist Javier del Valle, man, it just nails the biggest challenge they face. The atmosphere cannot be put in a laboratory. You just can't do it. You can't stick the planet in a beaker and run a controlled experiment. So climatologists have to be more like detectives, hunting for clues and piecing together evidence.
Right, so if you can't use a lab, what do? You have to observe. You have to watch the world as it is. And for a climatologist, that means trying to piece together the history of our climate by looking at data, and I mean data that goes back a very, very long time.
30 years. That's the magic number. The World Meteorological Organization says that's the absolute minimum period you need to reliably define a region's climate. And here's the kicker. For that data to be worth anything, it has to come from the exact same spot, unchanged. Because if you move a weather station even a little bit, you can throw the whole data set off. And to build that fingerprint, scientists are tracking all this stuff, and a lot more. We're talking precipitation, not just how much, but when it falls. Temperature, the average, the high, the low, the winds, the humidity, the clouds. It's like collecting all these little data points year after year to create a really detailed profile of a place. You know, what's really wild when you look at a timeline like this is just how new all our good tools are. The thermometer wasn't even invented until around 1600. And this explosion of satellite data, that's super recent. For most of history, we were basically flying blind, working with just little fragments of information.
So imagine you're a scientist a few hundred years ago. You have to be a detective. You might read in a historical record that a river froze over or that a harsh winter killed thousands of sheep. You know something big happened, right? But you don't know if it was minus 20 degrees or minus 30. It's a clue, but it comes with these enormous margins of error.
All right, let's zoom out and look at the big, natural pieces of this climate puzzle. These are the fundamental forces, the absolute titans that have been driving our climate for millennia. Long before humans were even a factor. Okay, so these are kind of the ground rules of climate set by geography. Where you are on the planet, your latitude. How high up you are, your altitude. And even the mountains around you, which way they face can create a totally unique climate. These set the stage. But there's another huge player that influences all of them. Yeah, thermal inertia. It sounds complicated, but it's actually pretty simple. The ocean is like a giant, slow-charging battery for heat. It takes forever to heat up and forever to cool down. That's why if you live near the coast, your winters are usually milder and your summers are cooler than for someone inland. The ocean is basically acting like a giant temperature regulator, smoothing out all the crazy extremes. And it's not just sitting there like a big tub of water. The ocean is active. These massive currents are like global conveyor belts, constantly moving heat from the equator towards the poles and cold water back again. They're working to balance the Earth's temperature, stopping any one place from getting impossibly hot or impossibly cold. And this is the perfect illustration of that power. Look at coastal Norway. It's way up north, but because it gets bathed in that warm water from the Gulf Stream, its winters are surprisingly mild. Now hop across the Atlantic to the exact same latitude in Canada.
It's brutally cold there in the winter. Why? It's getting hit by the cold Labrador current. Same sun, totally different ocean current, completely different climate. But in the grand scheme of things, very recently, a new piece has been dropped onto the puzzle board. A brand new factor that adds a whole other layer of complexity. And that new piece is us. And our impact runs the gamut, right? On one end, you have pretty small local changes. You plant a forest, and maybe that boosts local humidity a bit, makes it a little rainier. But on the other end of the spectrum, you have these much, much bigger ambitions, what's called geoengineering. And as the expert in our source material calls them, these are pretty concerning ideas about intentionally altering the climate on a massive scale. 52. Just let that sink in for a second. That number might really surprise you. But this is not some sci-fi movie plot. According to Spain's National Weather Agency, AMS, more than 50 countries have officially recognized programs right now trying to develop technologies to control their local weather. And you can imagine this kicks up some serious geopolitical dust. The source material uses this perfect example. What China manages to make rain in its territory is rain, according to India, that it is taking away from its territory. I mean, if you can literally make it rain over your country, is your neighbor going to accuse you of stealing their water? Because the atmosphere, it doesn't really care about our borders, does it? So let's step back. We've got geography, we've got the oceans, we've got human intervention. With all of this incredible complexity in the mix, trying to boil the entire climate down to just one single cause, well, that can be more than just simple. It can be dangerously misleading. And to really drive this point home, the source we're looking at uses this really interesting analogy. It compares what it calls the oversimplified CO2 theory of climate to the old calorie theory of dieting. Calories in, calories out. The argument is that just like our bodies are way more complex than that simple math, the Earth's climate is far too complex to be reduced to just one single variable. And following that line of thinking, the source really emphasizes how important precise language is here. It makes the point that CO2 isn't a pollutant in the traditional sense, but a gas that is, and I quote, fundamental and indispensable for life. The argument here is about being really careful and specific when we talk about the components of our incredibly complex atmosphere. And all of this really leads to the source's big takeaway, a call for what you might call scientific humility. The argument is that we have to be honest and upfront about what we don't know. There are still, quote, many things that we do not know about how our atmosphere really works, and that true science means always being open to new information, that the case is never really closed. So this leaves us with a pretty big question to think about, doesn't it? As we get better and better at understanding this incredibly complex climate puzzle, what are we going to do with that knowledge? Are we going to choose to be careful stewards, preserving its natural complexity? Or are we going to risk trying to control it, with consequences that are, frankly, impossible to predict? Thanks for joining us for this explainer.